So the last topic we're going to look at related to energy is what is known as power. It's not too complicated. If you already have energy down, then power should not be much of a problem for you. We define power as the rate of work being done. So power, we use a capital P for power. A lowercase p is for momentum, so use a capital P, please. So it's the rate, which is the work over the time. So we already know how to calculate work. Now all we have to do is divide by time. Work we can also get by doing force times distance. So that's all over time. And distance over time gives you velocity as long as that velocity is constant, or even if it's not constant, if it's the average velocity, which we denote with this bar over it. So this is another way to find power if we know the force acting on an object and the average velocity of that object. That will also give us the power rating. Another way to think about power that's often useful, since work is the transfer of energy, we can think about this as the change in energy over time, or the rate of change of energy. So that's what power is getting at. If we look at the units, work and energy are both measured in joules. Time is in seconds, so power is measured in joules per second. And this, we redefine a unit. 1 joule per second is equal to 1 watt, which is a capital W. So 1 watt of power. You've probably seen wattage ratings on different devices you have at home, like 60-watt light bulbs, the old incandescent ones. So a 60-watt light bulb is using 60 joules of energy every second. And you might think, holy crap, that's a lot of joules going by every second. But a joule is actually a pretty minuscule amount of energy. So that's 1 watt is pretty small. Plenty of devices use thousands of watts. Like your microwaves are usually about 1500 watts. So they're using a whole lot more than that little light bulb used. Let's look at a couple of examples on how to calculate using power. So you might have something simple, like let's compare lifting a 20 kilogram box 5 meters in the air and doing that in 10 seconds versus lifting a heavier box, 50 kilograms, 5 meters in the air. Oop, not 50. Erase, goodbye 0. And let's say that we take a little bit longer to do that, maybe 30 seconds, stop and rest or something for a while. Alright, so power, you can look at this a couple of ways. You can look at the work being done. The work is going to be the force. Well, the force is equal to gravity, so 20 times 9.8. So you could say the force times the distance over the time. So you'd have 20 times 9.8. times the distance of 5. Or another way to look at it is you could just look at the change in energy. Well, the change in energy is gravitational energy, so that's mgy. Well, that's going to be the same calculation, 20 times 9.8 times 5. So either way, we're going to have 20 times 9.8 over 5, and let's just write it one more time in case you haven't seen it enough, divided by 10. And that is going to give us a power of 98 joules per second, or 98 watts of power required to do that task in that amount of time. I'll call this P1, call this situation 1, situation 2. In the other situation, we're going to have the same calculation, either way you want to look at it, but now we're going to have 50 times 9.8. We have a heavier box, requires more force to lift. Still lifting at 5 meters, so maybe we're lifting it upstairs or something. But this time we do it slower, so 30 seconds. You plug in those numbers there, and you end up with only 81.7 watts. Now I'm kind of cut off there a little bit. Now the energy, or the work done, was greater. In this case here, that work is bigger than this work. Obviously, it's over twice as much work. But because we took over twice as long, it was less power expended to do that. Alright, let's look at one other example. Let's say we have a car that is accelerating from 20 meters per second, so that's our initial velocity. and it speeds up to, what did I write down earlier? 35 meters per second. The mass of the car is 1,000 kilograms, and let's say that it takes 5 seconds to do that, to accelerate from 20 to 35, and we want to know the power it takes to do that. Now you could, I guess, find acceleration, and then you could find the force, and you could find the distance it took, and then do force times distance over time, but that's probably a longer way around it. The approach I would use would be to look at the change in energy, and the time it took to change energy. In this case, the energy that's changing is the kinetic energy, so we'll say the final kinetic energy minus the initial kinetic energy over time is going to give us power. So that's going to be 1/2 mv final squared minus 1/2 mv initial squared over t. So we're going to have 1/2 of 1,000 times 35 squared minus 1/2 of 1,000, and you can factor out the 1/2 times 1,000 if you'd like, times 20 squared over a time of 5 seconds, and that, when you plug in all your numbers, gives you 82,500 watts, which might seem like a rather large number, but for cars that's really quite typical. That's not that much. I will make one comment. I mentioned earlier you could factor out this 1/2 times 1,000. A common mistake, if you do that, you've got 1/2 times 1,000, and then I've seen a lot of students, they take 35 minus 20 and then square it. Do not do that, okay? That is not the same algebraically as factoring out that 1,000 and doing 35 squared minus 20 squared. Okay, this is the correct way if you want to factor it out. Do not do it this way. Okay, so back to this 82,500 watts. If you've heard of the power ratings of cars, we don't typically measure them in watts because we would have these huge numbers. What we usually use is horsepower, and it turns out that 1 horsepower is equal to 746 watts. So this here is only about 110.6 horsepower, which is not a huge horsepower rating for a car. And the history of this horsepower unit is kind of interesting. It actually came, the watt is named after a guy named James Watt, and he was a British engineer, inventor, scientist kind of guy. And he is actually the one who gave us this horsepower unit. What he was doing, he was improving upon the steam engine, and he wanted to sell it to different industries to use to replace horses, because at the time they used horses to pull their mill wheels and to lift water up and all kinds of things they used horses for instead of motors. Well, he wanted to be able to say how many horses they could replace if they bought this motor. So he actually went and he measured, and originally he measured several ponies and found that they could on average lift 220 pounds 100 feet high every minute over the course of a 4-hour work period. They could sustain that at kind of an average rate. And then he figured a horse could do about twice that. And so that's how he came up with the equivalent for his engine here, was he actually measured ponies and horses. Turns out horses can actually have about 15 horsepower for short periods of time, for a few seconds. But over hours, that James Watt's measurement is actually pretty accurate. That's about how much work a horse could do for a sustained period of time. Alright, one other thing I wanted to look at when we're on the topic of units is something called a kilowatt hour. So this is when you're older and get an electric bill, your usage will be measured in kilowatt hours, which is kind of a strange, ugly unit. And if we look at this, the kilo just is multiplying by 1,000. So this is watts, which is power, times hours, which is time. And we said that power was change in energy over time. So power times time is our change in energy. So this unit here, a kilowatt hour, is actually a measure of energy. And the reason they use it is because if you're using a kilowatt of power for an hour, then you will use that much energy. But if we wanted to convert that to joules, you're going to have to look at watts or joules per second, and this is thousands of joules per second, and then hours. So you're going to have to do some unit conversion if you want to figure that out. But that's an interesting unit that the electrical industry uses. All right, we will see you next unit. Take care.